in this particular problem, it says a person purchased a slot machine and tested it by playing it 1,261 times. There are 10 different categories of outcomes, including no win jackpot, win with 3 bells, and so on. When testing the claim that the observed outcomes agree with the expected frequencies, and assuming it isn't the same frequency for each category, they would have to give us that. The author obtained a test statistic of chi-squared equals 15.087. Use a 0.025 significance level to test the claim that the actual outcomes agree with the expected frequencies. Does the slot machine appear to be functioning as expected? Okay, so the test statistic is exactly what they just gave us. We don't have to calculate that. It's there. The test statistic would always come from the test. And since they did not give us the test data individually, they gave us the test statistic was 15.087. The critical value, however, is not given. Now, we could go to a chi-squared distribution table, in which case for 0.025 being the amount in the critical area, we're going to have to look all the way down here at 0.025. There are 10 different categories. The degrees of freedom with 10 categories is going to be 9. So we look in row 9, and we're going to find the 0.025. So we go all the way over 0.025. The critical value is going to be 19.023. Now, another way we could have gotten this would be to go ahead and go into StatCrunch, go to Stat, Calculator, chi-square. The degrees of freedom is going to be 9. We want to know what the chi-squared value is if the amount of area to the right of the chi-square of the critical value is 0.025. And we get 19.023. Same as here. Because the test statistic is closer to 0 than the critical value, it is not out there in the tail, we would therefore not reject the null hypothesis. There is not sufficient evidence to warrant rejection of the claim that the observed outcomes agree with the expected frequencies. So the slot machine appears to be functioning as expected. Now, in a problem where we have to come up with the test statistic ourselves, in this problem, a person randomly selected 100 checks and recorded the cents portions of those checks. The table below lists the cents portions categorized according to the indicated values. So if it's 0 to 24 cents, there were 51 of those, 25 to 49, there were 14, and so on. The person expected that many checks for whole dollar amounts would result in a disproportionately high frequency for the first category, but do the results support that expectation? Well, there are actually nearly over half of the 100 checks fell in the first category where there would be 0 cents, that's therefore whole dollar amounts. But to actually find out, let's open this in StatCrunch. To get the test statistic, go to Stat, Goodness of Fit, chi-squared test. Our observed frequencies are the numbers. We're going to use a 0.05 significance level to test the claim that the 4 categories are equally likely. Now, if there are given frequencies for each of the categories, you select the column that those are located in. But if we're saying each of the categories is equally likely, just hit all the cells are in equal proportion. Compute. So our expected value, if they're in equal proportion, would be 25 in each category out of the 100. Our observed values were given here. The chi-squared test statistic is 37.36. The critical value for that, let's go back to the calculator for chi-squared. We want a 0.05. We've got 3 degrees of freedom because there are 4 categories. We want to have greater than 0.5 to the right of the critical value. So the critical value is going to be 7.815 because the critical value is here. And our test statistic is way, way out here. I mean, this is 20, it doesn't even go out to 37. Therefore, our conclusion is going to be that we reject the null hypothesis. There is sufficient evidence to warrant rejection of the claim that the 4 categories are equally likely, and the results appear to support the expectation that the frequency for the first category is disproportionately high. Since all the chi-squared value tells us is that at least 1 category is off the mark from what the expected frequencies were. We can look at the actual numbers and see that over half of the frequencies, over half of the checks fell in this category. This one's not far off from 25, so a lot of these came out of these 2 categories. So the chi-squared value simply tells us that we need to look harder, that something is off compared to the expected frequencies. Now, in this problem, they were not kind enough to give us a way to load this into StatCrunch the way they usually do. So I could just type these in. I can just load up an empty StatCrunch sheet. The observed frequencies for the outcomes of 1, 2, 3, 4, 5, and 6 for a die, and I don't actually have to put those in. They're not actually going to be used in the calculations. Those are simply the names of the categories. Those are the things that a die could land on. After rolling it 200 times, he tried to fill it with a lead weight to throw it off, and then roll it 200 times, and he got, I'm just going to add these in, 28, 29, 42, there were 42 threes, 38 fours, 28 fives, and 35 sixes. And then we're going to use a 0.01 significance level to test the claim that the outcomes are not equally likely. Well, that's not our null hypothesis. Our null hypothesis would be that they are equally likely, because that's the only way the null is allowed to work. So let's just see what kind of a chi-squared value that we get here. Stat, goodness of fit, chi-squared test. Our values are in the first column. We're going to claim that they're all equally likely would be the null hypothesis. That means that we would expect 1/6 of each of the 200 to land in each category. Instead, we got these. How far off is it? What the chi-squared value does is it takes the difference between the observed value and the expected value. It gets that difference and squares it to keep negatives from canceling out positives, and then divides it by the expected value to see what proportion of the difference is to the expected value. And then you add all of those together. So the actual test statistic that we got here was 5.26. You can see that that's right here. The critical value would come from the calculator just as before, except that this time we would use 0.01, and there would be a difference of frequency, degrees of freedom of 5 because there are 6 categories. And the result, after finding that the critical value was 15.806, is that the test statistic is to the inside of that, it's to the left, therefore we do not reject the null hypothesis. Now in this problem, the table below lists the number of games played in a yearly best-of-7 basketball championship series, along with the expected proportions for the numbers of games played with teams of equal abilities. So for best-of-7, if one team wins 4 in a row, they've won, the other team could only get 3. So there could be 4 games played, 5, 6, or they might have to go all the way to 7 games. Use a 0.05 significance level to test the claim that the actual numbers of games fit the distribution expected, indicated by the expected proportions. So here are our expected proportions. Here are our observed numbers. This is our category labels. Naturally, the null hypothesis is going to be that the observed frequencies equal the expected proportions. In a chi-squared game, what we are looking for with chi-squared is that at least one of the frequencies do not come out to be the expected proportions. So in this case, when we load this into our goodness of fit chi-squared test, our observed frequencies are the actual contests. Our expected values are in the expected proportions. In this case, it's not a case of all the cells are equal. So if we compute this, our chi-squared value turns out to be 6.92. So the test statistic is going to be 6.592. The p-value, as you can see, is 0.0861. Because the p-value is over 8% compared to a 5% significance level, we don't have to get the critical value. We know that the probability is higher than what we need for a significance level. Therefore, we will fail to reject the null hypothesis. There is sufficient evidence to warrant rejection, no. Fail to reject the null hypothesis, there's insufficient evidence to warrant rejection of the claim. So that's all you have to do on the goodness of fit tests. With StatCrunch, it's actually pretty easy. Let me know if you do have any trouble with it, and I'll see you later.